here, and if it continued on, it would continue to the other side of the map here. But it's actually right in the very middle of the Pacific plate, and you can see the little volcano in the middle of Hawaii here. It's not at any plate boundaries, so we're not talking about any plates coming together, any plates separating apart. It's just basically a really hot spot underneath there. It's breaking through the surface. All right, so oceanic convergence, we've looked at that. The last type of convergence you can have is two continental plates coming together. Now, this doesn't happen a lot. There's only a couple spots where it does happen. But you have these two really thick continental plates. It's like two semi-trucks running into each other. Well, what happens? Well, generally speaking, one's not going to go under the other because they're just so big. They're just going to be a just big crumpled up mess. They're not going to, go under. They're just going to run into each other and make a big giant mess. So this is what happens in a few spots, and we'll try to find some examples of it. You can see there's no really distinct things going on. There's no subduction. There's no push or anything like that. They just kind of run into each other. And this is the idea. If you think about taking two rocks and you push them together, well, what's going to happen? They're rocks. They're extremely hard. They just bang into each other, and that's it. Maybe you can chip pieces off of them. But when we start talking about really, really large forces, over really long periods of time, rock will actually start to bend and fold and things like that. So you can see the layers of the rock here. This would normally just be kind of flat layers of rock. You can see them flat over here. But once they start to push into each other, it bends and folds and all sorts of crazy things happen. You get earthquakes, and we think of rock as being such a static thing that can't really move or bend or fold. It's just really hard. But the amount of energy we're talking about here is enough to make rock actually bend and fold. So pretty amazing when you think about it. The best example of this, I'm not even going to make you find it, but I guess I should make you find it. Find an example of continental convergence on your map. Are there any examples of it? It gives you the example of the Himalayas here. Does it happen anywhere else? Is there anything else going on? So when you end up with these two big, thick plates running into each other, magma doesn't ever really form because you have these really thick plates that magma can't rise up. You end up with not as much going on. So if we jump back to the image here, we're looking for convergence. So that's a line with the little triangles on it, but with two continental plates. So you're looking for the line with the triangles happening on land somewhere. So Scotia Plate is right here. So this is an oceanic plate. So this isn't continental convergence, because we don't have a continental plate here. This is a nice thin oceanic plate. The only place it really happens is right here, just above my head. The Eurasia plate and India. And India is actually a bit of a smaller plate, but they've showed it as the Indo-Australian plate. But India was its own plate. And India is running into Eurasian plate right here. And this is here's another example of it. And these are the youngest mountain ranges in the world. This is the Himalayas right here. So this is India, you have China and sort of Tibet kind of jammed in here. And this is the highest elevation above sea level. So Mount Everest is 8,848 meters above sea level. And because those plates are still moving, they're still coming together, every year Mount Everest gets a little bit taller. We're talking millimeters, but it is getting taller. So you end up with weathering, making it smaller, and it's trying to rise, and these plates are coming together, but all of those mountains in the Himalayas are actually getting taller each year as those two plates run into each other. So if you were to climb Mount Everest today and somebody else, your friend, climbed it tomorrow, they're technically climbing a taller mountain. It wouldn't be measurable, but they're technically climbing a taller mountain. So that is continental convergence, and you can see all these mountains that get formed as a result of it. And the Himalayas is the best example of that type of thing. So there's continental convergence. So the three types. of convergence. You have two oceanic plates, you have a continent and an oceanic plate, or you have two continental plates. Those are the only three things that can happen. The last type of boundary we're talking about is a transform boundary. So this is, instead of plates running into each other or spreading apart, they're actually moving side by side, so they're sliding past each other. And there's a really famous example of this in kind of our area, and we'll talk about that here in a second. But transform boundaries are the result in lots of earthquakes, because these plates, they start to move, they're going in different directions, and then they'll slip, and then they'll lock up again, and energy will build and build and build, and then they'll slip. And each time you get a slip, that's what causes an earthquake. So because you have two plates sliding past each other, you're not going to get volcanoes. There's no weakness for magma to rise up. They're not spreading apart, allowing magma to rise. One's not going under, creating magma to rise. You just have these plates sliding past each other. So you get lots of earthquakes, but not very many volcanoes. And the famous example of this one is the San Andreas Fault in California. Basically runs really close to LA and San Francisco, right kind of through the heart of California. And that's why the California area is so prone to earthquakes, because you have these two plates sliding past each other. And every once in a while you get a very strong earthquake as a result. If you get lots of small earthquakes, that's a good thing. Lots of energy is being released in really small increments, perfect. When you don't have earthquakes for really long periods of time, that's when bad things are going to happen, because you're going to get a big slip and you're going to get a big earthquake. And you'll notice the symbol for this is these little arrows. So you'll get a line with two arrows going in opposite directions on either side of the line. So that is a transform boundary. Let's look at an example. Well, here's an image. This is the actual San Andreas Fault here. You can see running down the middle of this picture. And this one plate here is going down. This plate here is going up. And it's a physical line, which you can actually see from the sky, which forms this boundary between two plates going in two different directions. So there you go. Transform boundaries. They are just a line with arrows on either side of it. I guess it's worthwhile to just jump back to our main sort of map. This is our neck of the woods here, the Juan de Fuca plate. You can see a transform boundary right here. You have your two arrows. There's another one just a little bit north off the coast of BC, just next to Haida Gwaii, Queen Charlotte Islands. Another transform boundary here. And if I go back even further, we look at the giant map again. You can see right through the middle of California down through Baja, Mexico. You end up with this big transform boundary on land. Now, if you fall between the plates, that implies that there's somewhere to fall. You can literally go and stand on this transform boundary in the San Andreas Fault. You could stand on it. You could put 1 foot on one side, 1 foot on the other. Remember, these are two continental plates. They're kilometers thick, and they are butted up right next to each other, and they're really, really pushing into each other really, really hard. So it'd be like you stepping between my hands right now. You wouldn't just fall between them. The pressure that's built up between these things is absolutely immense. Even though one's going one way and the other's going the other way, if they were far apart, they would just move past each other and we wouldn't end up with any earthquakes. They would just be like, oh, this is great. We can just move past each other. But they're being pushed into each other really hard, and they slip and slip and slip. Even if you went to the Rift Valley in Iceland, where those two plates are moving apart because of divergence, you can stand between them and nothing happens to them. So do I think Superman could? I don't know the limits of Superman's power, but I would assume that he probably couldn't. I don't know. Although he spun around Earth the wrong way to make it go back, maybe he can. I'm not sure. You'd probably have to ask an expert on it. All right, so back to the idea of symbols. You guys, I kid you not, on the provincial exam or test, there'll be questions that say, you know, is an earthquake likely to happen? Not an earthquake, that's a bad example. Is a volcano likely to happen in California? So you go to California and you go, okay, here's California, And oh, that's a transform boundary. So you can see the transform fault here. And do you think an earth or a volcano will form there? Well, no, there's nowhere for the magma to rise up. So they ask questions like that. You need to be able to use the information here on your map to identify the type of boundary, divergent, convergent, transform, and identify things that are happening as a result of it. If you have subduction happening, like off the coast of South America, here's a great example of the Nazca Plate getting subducted under the South America Plate. You get this subduction happening, this Nazca Plate's going under it. Where you're going to get volcanoes? Yeah, that plate's going to melt, it's going to rise up, you're going to get a big chain of volcanoes. That's the Andes right here. So it's going to ask questions like that. Can you identify what's going on in terms of the map and what happens at those types of boundaries? So that's essentially the tectonic plates stuff. Now, the section in your notes continues on with volcanoes and earthquakes, but I think it's just a lot. So what I've done is I've broken it up into two sections. So 10.2, we have the tectonic plate stuff, and then we're going to talk about volcanoes and earthquakes after. So it is 10 after 10 right now, almost. What I'd like you guys to do is I'm going to give you, let's go with 30 minutes. I'm going to give you guys 30 minutes to go and do the tectonic plates activity from the course. So if you've done it, you can just continue on in the notes or whatever you want. But I'm going to give you guys 30 minutes to go through this activity, plate tectonics. Print it, do it on the computer. I don't care. After that 30 minutes, I'm going to get you guys to come back. And then we're going to talk about earthquakes and volcanoes for a little bit until the end of the block. And then next day, we do have a double block again on Wednesday. But it won't take, pardon me, it won't take us that long to get through it. So we'll get a jump on some of Wednesday's stuff after this like 30-minute break. So does anybody have any questions before we take a bit of a break here? I'll give you guys half an hour to do this plate tectonics thing, grab a snack, drink, whatever, and then we'll, you can draw it by hand in Word. Just grab the little pen and draw it. It doesn't have to be perfect. The plate boundaries, if you have a thick thing and a little thing going underneath it, I don't mind if it's drawn on the computer. It doesn't matter much to me. If you want to print it and do it by hand, great. I'm not saying you have to submit it right now. I'm just giving you time to do it. And then you hand in the plate tectonics assignment, this Word document behind me, with the learning guide at the end of Unit 10, like we've been doing with our assignments. So I get Mr. Ross to put up that 30 minutes. I will see you guys back here in a little while. Thanks. Hi guys, welcome back. If you can fire me off a green check mark, just make sure everything's good, and then we'll just continue on. I see you guys had a few issues and some questions and stuff, so I'll get to those for sure. Just want to make sure everything's good. Perfect. All right, so we're okay. The little error that's coming up is saying, I can't, open this or access this. It's just kind of like one of those things your computer's warning you. It's like a Java thing, and so if you run it, it's not going to install a virus or anything on your computer. The other thing that you could be running into in terms of troubles is where it says click to run, it doesn't work, and then if you click above it, it does work. So that's kind of silly. I don't know why it doesn't work there, but if you click above it, it should run as just fine. So hopefully that gets rid of a few of your questions. Abby asking a question about why the Earth's crust is less dense than the core. Can anybody answer that question? Anybody have any idea? I know, it's kind of weird. I don't know why it's showing up like that, but it is. It is what it is. I'm sorry. Anyone think of something, why does it say tectonic thing is overdue by 4 days? It could have maybe when I opened it, put in a due date. Just ignore it. I'll go and change it later. I'll put in a due date of Friday for it. You're trying to update your Java? Yeah, I'm sorry. We're going to run into problems like that from time to time. So the more ironies you go further down. Think of maybe getting back to Abby's question. Think about in terms of general just densities. Think about things in your everyday life and their relative densities. So don't think specific to the layers of the Earth. Just think in general. You learned about density in grade 8, I think. What do you guys know about density? It's actually kind of, once you think about the answer, it might be like, oh, really? Yeah, that's exactly it, Ava. If you have something that's less dense, it floats. So if the surface, if the crust was more dense than the core, you would end up with the crust kind of sinking down through the middle of the Earth and kind of settling down in the middle of the core. I know, it's kind of one of these light bulb things. It totally makes sense though, right? So when we think of rock, we just get into this mindset that rock is so hard and it can't move and you can't bend it and things like that. But the Earth has a tremendous amount of energy in it. It can force this rock to melt and fold and bend, and it can actually liquefy it and turn it into a magma. If it makes the surface, it becomes lava. And you end up with this really crazy things that just don't make sense in our everyday lives. Our normal temperatures and pressures on the surface, we can't really fathom with our experience of what is actually happening below the surface, because there's sort of nothing in our everyday makeup that would allow us to kind of, experience what it would be like to be hot enough for rock to melt, or enough energy or force to bend rock, to fold rock. So you end up with these really crazy things. So so hopefully you get the idea there that the continental crust is less dense. It floats kind of on that asthenosphere, the lithosphere, that hard crust, kind of floats up there. So there you go. Just out of curiosity, did you guys have enough time to finish that? Almost finish it? Where are you guys at with that? I'm just trying to plan out today and next day to kind of see what we can cover in terms of material. No, didn't finish it. Okay. So you guys will need some more time for that, which is fine. The next section isn't really its own section. Half left, almost done. Cool. So 30 minutes wasn't quite enough, but you're nearly there. That's all I wanted to know, which is great. Taylor, you're still working on downloading it. Okay. Perfect. I'm going to just mosey on over. The next section isn't really a section. It's just the 10.2 continued. And it's kind of a fun section because everything we talk about in earth science takes really long periods of time. But earthquakes and volcanoes both happen in sort of a human time frame. When you watch a volcano erupt, magma comes flying out and things are happening in kind of a human time scale. So it's really cool. Earthquakes happen in a human time scale. They'll last for, a minute. That's an earthquake. Awesome. You can experience that. Whereas right now I'm standing on the North America plate and it's moving at about 2 centimeters a year. In my lifetime, if I'm lucky enough to live 100 years, it's going to move about 2 meters in my entire life. Nothing really exciting is going to happen. But these things happen in a human time frame, so we can experience them. And I know it sounds silly, but if you've ever experienced an earthquake, it's scary and it's amazing all at the same time. So we're going to talk a little bit about volcanoes and earthquakes. There's a little bit of notes here, but the majority of it is just me blathering on about really cool things that I find really interesting, and I hope you find them interesting as well. So earthquakes are extremely difficult to predict. That is why they're so devastating, and that's why they can cause so much damage. We can't predict very accurately when they're going to happen, how big they're going to be. We give these things time frames. We say, well, the Juan de Fuca plate's being subducted underneath the Pacific plate off of Vancouver Island, and an earthquake hasn't happened there in, this many years. And if we look in the past, in the geological record, we can see that an earthquake happens maybe every 1,000 years. So if we're past 1,000 years since the last earthquake, well, we know we're due for another one. And this is kind of what's happening right now. I don't have the exact dates for our area here, but Vancouver, Pacific Northwest, is due for an earthquake. There hasn't been a major earthquake for a long time. So we know that energy is building between the plates and it's eventually going to slip and let go. And it's just a matter of time before that happens. So we end up with these really long distances, these plates sliding past each other, either going under, sliding next to each other, or into each other. And the energy builds up. You imagine putting really long things together and pushing at them really hard, and they're going to slip eventually. So there's some important vocab you need to learn. Just two things. When you talk about earthquakes, there's two important words. The first word is the focus, and that is exactly in this fault line where the earthquake happens. So this fault is a place between two plates. It's exactly where it happens. Well, we don't live, 100 kilometers or 10 kilometers down in the earth, so we don't really care as much where the focus is. What we're concerned about is where the epicenter is, and the epicenter is the point on Earth's surface directly above the focus. So we're always interested in the closest city to a major earthquake or anything like that. So there you go. The two important words for earthquake are focus and epicenter. We'll look at a few other ones, but they are very similar in their meaning. They're both where the earthquake happened, but where the one on the surface is the epicenter, the one under the surface is the focus. So there you go. That's kind of a boring slide. Apparently I didn't have time to put a picture in this one. Earthquakes happen at different depths. So when you have a plate getting subducted under another plate, you end up with earthquakes, very shallow ones up at the top. You can end up with earthquakes well down into the earth. The shallow earthquakes have a really, their focus is close to the surface, so the energy, causes more damage because it doesn't have to travel through as much rock to kind of get dissipated. But if you have a really deep earthquake, then generally speaking, they're not quite as devastating because there's more rock for that energy to kind of get dissipated in. If you think about sound is a transfer of energy. I vibrate the air, it travels to your ears, you hear it, it vibrates your ear. Well, if I'm talking to you from like outside of your front door, well, the door is there and you can't hear me quite as well because the door is kind of muffling that energy that's getting transmitted. Same idea with earthquakes. The deeper the focus, the less energy gets transmitted, gets dissipated through all the rock. Why don't we have global earthquakes, Alex? What do we think? Where do earthquakes happen? Well, earthquakes happen at fault lines between two plates. So when two plates meet, the plates are all going in different directions, different places at different speeds. So you wouldn't end up releasing energy in one spot. And then that, I guess, what I'm kind of implying from your question, or what I think you might be implying, is like an earthquake here causes an earthquake somewhere else, causes an earthquake somewhere else. There's just not enough energy released for it to travel far enough to hit another fault line, I guess might answer your question, or it might not. So subduction zones because of the way the plates interact, you have shallow earthquakes, you can have really deep earthquakes. The volcanic hotspots, which we haven't talked about yet, but they can produce earthquakes as well because that magma pushing up. It might be theoretically possible, I'm not sure. I'm thinking the amount of energy released from an earthquake might not be enough, but it could happen, I'm not sure. What does happen along a single fault line is you can get a big earthquake in one spot, and it can release tiny little earthquakes all the way along the fault line. So a common one that just happened was the Japanese earthquake about 10 years ago or so. We talked about Japan moving, like 2 meters closer to North America. So normally plates move 2 centimeters. It moved 2 meters in a second, instead of moving 1 centimeter or 2 centimeters in a year. So this is the type of energy that's being released when these plates build, and they slip, and Japan moved closer to North America by about 2 meters. Could a nuclear explosions cause earthquake? Nuclear explosions are pretty small relatively compared to the energy released in an earthquake. Earthquakes release, thousands of nuclear explosions worth of energy. These are the types of forces that it's just almost unfathomable how big the energy is released in an earthquake is. Nuclear explosions are small compared to them, if you think about it that way. There's one exception, or a couple exceptions. We'll talk about them later on. All right, so here's a map, and I haven't drawn plate boundaries on here with these red dots or anything, and the legend's really hard to read, but it doesn't really matter. What you need to know is that this map is showing the depth of earthquakes. So red dots are very shallow earthquakes, and then let me get my color straight here, yellow are deeper, green are deeper, and blue are the deepest. So the focus is the deeper. So red is very shallow. So if we took a map of the Earth and we measured every single focus and we put its depth, this is what this map is showing. Now, you can see that earthquakes happen at the fault lines where the plates meet. So you notice down the Mid-Atlantic Rift here, you end up with all of these shallow earthquakes. Why don't you have deep earthquakes at a rift valley? Let's see if we can put some ideas together here. Why are there no blue dots here? Why are there no green dots here? Why do we only have red dots? And then our little neck of the woods here, we have red dots again. Red dots here, red dots here. The crust is very thin, that's right. Generally speaking, the earthquakes are pretty shallow in the Vancouver area. The crust is thin. You have these two plates moving apart, right? So the magma is rising up between them, causes lots of small earthquakes, but there's no subduction happening there to cause really deep earthquakes. If we think about, subduction, you're going to get a plate going under, you're going to have earthquakes happening way down here, really deep foci? I don't know if that's plural or singular, I'm not sure. Doesn't sound right. So you go here where this Nazca plate is going under the South America plate, and you end up with these really deep earthquakes that are further inland. And then look over here, you end up with extremely deep earthquakes where you have subduction happening. This is New Zealand area here. So this is kind of what's happening. This is an example of subduction where these earthquakes are occurring. So you have this is Nazca, so that's what we're just looking off the coast of South America, the Andes Mountains there. You have these really shallow earthquakes happening right here, and then you have your mid-range earthquakes here, and then you have these green guys, and then the blue ones are these really, really deep earthquakes that have really deep focus, and very relatively small amounts of damage. But look at how far inland we are here. This is 1,000, that's 500 kilometers right here, 1,000 kilometers. So we're only a couple hundred kilometers from the ocean, our plate. So we're talking about like earthquakes that would happen in maybe 1,000 kilometers. We'd be looking close to the edge of Alberta maybe. The Pacific plate is kind of riding on top of that other plate. So you can end up with earthquakes happening thousands of kilometers from the actual subduction zone, the actual trench that gets formed because of those plates getting slid under one another. So you can see the majority happen kind of in this area here. Very few deep earthquakes, but they do happen. All right. This is the notes just mention hotspot, but I think it's really cool. There's some really cool examples, so I'm going to talk about it for a minute. It's not a huge part of the course, but I find it interesting. So here we go. Abby, you were asking about this earlier. You said, is Hawaii an example of like convergent plate boundary or whatever? But if you look at Hawaii, it's right in the middle of this Pacific plate. So you end up with Hawaii, this hotspot, right in the middle of the plate. Another thing that comes up from time to time is the Ring of Fire. So the most seismically active and volcanically active region on Earth is this circle around the Pacific plate. The Pacific plate's kind of pushing into all the plates around it. And you end up with like Japan down through Philippines area, Indonesia, down New Zealand, and then up the Andes here, up North America. So you